Hey pre-cal, did y'all miss me? No. Okay. So I'm on 7-2 part 2, the examples, and I'm going straight to example B. I'm going to go ahead and just send you a picture of example A because it's pretty straightforward. But example B is asking me to verify that the matrices are inverses of each other. Okay, so inverses is the new part. So an inverse is what you can do to get back your identity. All right, and your identity is what you do to give you back what you started with. Okay, so what I'm saying to the cloud, if I was adding, right, in addition, the identity, the number that gives you back what you started with is 0, right? If I had a 5 and added a 0, I still have 5. It kept its identity, right? Or if I had a -7 and I added a 0, I'm still going to have -7. It kept its identity. For addition, the identity is 0. Okay? For multiplication, the identity is 1, right? Doesn't matter what number I have, if I multiply it by 1, I'm still going to keep that same number. Whatever the number may be, I don't care, 32,459. If I multiply it by 1, I still have the same thing that I started with. It keeps its identity. So for addition, your identity is 1. When I'm dealing with matrices, my identity is called the identity matrix. And it's listed, or it's named with an I and an N. And the N just stands for however many rows and columns it has. This is for a square matrix. So if I'm doing a 2 by 2, the identity matrix is just going to be 1, 0, 0, 1. If it were a 3 by 3, it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. If there were 5, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. All right, hopefully you're seeing the pattern here. Oh, I need another one. Okay, do you see it? Do you see the what's happening in all these? The pattern is I have a diagonal row of 1s. Yes? I have a diagonal row of 1s. So my identity matrix, and like I said, if there was just 2, it would be I2. And it's however many rows and columns you have. But what you're going to have is a diagonal of 1s. And when I multiply by the identity matrix, it is going to give me back what I started with. All right, again in the cloud, I can show you that even with this 2, 1, 3, 4 that I have. 2, 1, 3, 4. If I multiply the identity matrix by 2, 1, 3, 4, I should get back out a 2, 1, 3, 4. So let's see. If I go across and down, 1 times 2 is 2, plus 0 times 3 is 0. Across and down, 1 times 1 is 1, plus 0 times 4 is 0. Okay, across and down, 0 times 2 is 0, plus 1 times 3 is 3. And across and down, 0 times 1 is 0, plus 1 times 4 is 4. And when I simplify that, 2 plus 0 is 2, 1 plus 0 is 1, 0 plus 3 is 3, 0 plus 4 is 4. 2, 1, 3, 4, just like how I started. So it keeps its identity. Okay? So that, again, the identity matrix is just a diagonal of 1s. And it starts in the left, the top left corner, because that's where we start when we read, right? The top left corner. All right, all of that was just the cloud. So if these are truly inverses, which they are because I'm telling you to verify it, I'm not asking you, are they inverses? In example B, I'm asking you to prove it. I'm asking you to verify. So since they are inverses, that means when I multiply them together, they will give me the identity matrix. All right, that's how I know that they are inverses, and that's how I prove that they are inverses. This will be true for A times B. It will also be true for B times A. All right, so A times B, I'm just going to go across and down. 2 times 0.8 is 1.6. 1 times negative 0.6 is negative 0.6. Across and down. Again, each one has its own partner. So 2 times negative 0.2 is going to give me negative 0.4. And then 1 goes with the 0.4. That'll be a positive 0.4. All right. Now it's time for the bottom row. Across and down. The 3 multiplies with the 0.8. That will give me 2.4. And the 4 will multiply with negative 0.6. That'll give me a negative 2.4. Right? These are just like 24 with a decimal point. All right. Across and down. So the 3 goes with the negative 0.2. That gives me negative 0.6. And then the 4 multiplies with the 0.4. And that'll give me a positive 1.6. And when I simplify this, 1.6 minus 0.6 leaves me with just a 1. Negative 0.4 plus 0.4 gives me a 0. 2.4 minus 2.4 is a 0. And negative 0.6 plus 1.6 is a 1. That is the identity matrix. That is my diagonal of ones. All right, I said it should work with A times B. If I'm verifying it, we'll also work with B times A. B times A will also give me the identity matrix. But they told me to verify it, so I have to show it. Again, I like to write it with the B in the front. It's just easier for me to see the across and down that way, so bear with me. Negative 0.6, negative 0.2, 0.4. And A was 2, 1, 3, 4. Okay, so now for B times A. B times A. Across and down. 0.8 times the 2 is going to give me the 1.6. The negative 0.2 times the 3 is going to give me a negative 0.6. Across and down. The 0.8 times the 1 is going to give me 0.8. The negative 0.2 times the 4 is going to give me negative 0.8. And now for the bottom. Across and down. Negative 0.6 times 2 is negative 1.2. And 0.4 with the 3 times the 3 is a positive 1.2. Across and down. Negative 0.6 times 1 is negative 0.6. And 0.4 times 4 is a 1.6. So no, it is not necessarily all the same numbers as they were last time. Some of them match, some of them don't. But don't think that A times B is automatically B times A. We've already talked about that. It is not necessarily commutative. But in this case, the 1.6 minus 0.6 is 1. The 0.8 minus 0.8 is 0. The negative 1.2 plus 1.2 is 0. And the negative 1.6 plus 1.6 is 1. So I have proven it. I have verified. I have shown that A times B equals B times A, and they both equal the identity matrix. B2 is a star.